So in this video, we're going to define a few definitions of a Cartesian vector. So we're going to talk about Cartesian vectors in 3 dimensions. And the reason we're interested in using Cartesian vectors, we need to know about Cartesian vectors, is they allow us to add multiple concurrent forces, which basically means forces that are acting at the same point together in a very simple manner. So in order to use Cartesian vectors, we need to define our coordinate system first. So we're going to define, we will always use in this course and in most engineering courses, we're always going to use a right-handed coordinate system. So a right-handed coordinate system will have 3 axes. Okay, in 3D, we'll typically draw the x-axis on the bottom left, the y-axis on the bottom right, and the z-axis going vertical. So all the axes that I've currently drawn are the positive axes. Okay, and then we can also denote the negative axes with dotted lines. So to determine the direction of our given axes, we can use the right-hand rule. So a way you can think about this is if you took your right hand and you pointed your fingers of your hand along one direction, so that would be your x-axis. Right? Then if you bent your fingers at a 90-degree angle away, right, your palm would then align, and like the rest of your arm would align with the y-axis. Okay? And then if you stuck your thumb up in the thumbs up position, your thumbs up or your thumb would go along the z-axis. Okay? All right. All right. So if you're ever confused about which part of your hand should be the x-axis, which part of your hand should be the y-axis, one part of your hand should be the z-axis, just remember your fingers, your palm, and your thumb, and just put them in alphabetical order, and it will go follow the x, y, and z axes. All right. So what we can do is if we have our coordinate system set up for x, y, and z, and we have a vector, which we'll call vector A. All right, we can define vector A and any vector in terms of 3 subvectors. So we can have a part of vector A that goes along the x-axis, which we'll call vector AX. We will have a vector that goes along the y-axis that would be equal to AY, vector AY, and then we will have the last vector, part of our vector, which will be the vector that goes parallel with the z-axis, for vector AZ. Okay, so if we add these 3 vectors together, we will get our total vector, and this can be applied for any vector that we define in an XYZ coordinate system. So to help us define our vectors even more, we can use Cartesian unit vectors. So you may have used these in physics 191. So what these stand for are, we have vector I hat, which corresponds with the x-axis. Right. We have vector j, which corresponds with the y-axis. And we have unit vector k, which corresponds with the z-axis. So all 3 of these vectors of the unit vectors have a magnitude of 1. Right? And they act along their respective positive axes. So for vector I, it corresponds with the x-axis. It acts along the positive x-axis always. Vector j always acts along the positive y-axis. And vector k always acts along the positive z-axis. All right. So the benefit of using Cartesian vectors representation is we can now split our vector A into 3 components. We can split it into the x component, ax I, all right, which is where ax is the magnitude of vector A along the x-axis, and then I is the unit vector along the x-axis. And we can do the same process for AY and for AZ, all right, where AX, AY, and AZ are the magnitudes of our vector A along the X, Y, and Z axis, and then I, J, and K are our unit vectors. So if we have our vector defined in this manner, we can it's really easy to find the total magnitude of the vector. So we can, so if we have our vector A, which we defined as A of x, of I plus A of y, j plus A of z, k, if we have this vector defined in our Cartesian coordinate system, we can very easily calculate the total magnitude of that vector, or the length of the vector, which would just be equal to a which is going to be written with double brackets, or just the letter a, and we can write it as being the square root of a of x squared plus a of y squared plus a of z squared. So we can write so we can draw our magnitude a, our vector a, in terms of ax, ay, and az. So if we draw that out, you would get a of x, a of y, and we would have a of z. All right. So the other term that might come up or might be asked is sometimes you might be given the dimension of a length that's in the xy plane, but it's not in, it doesn't really relate to x or y directly. So sometimes we'll call this value a prime, where we can say that the magnitude of a prime is going to be equal to a of x squared plus a of y squared. All right, so that's just the 2D Pythagorean theorem. All right, and then so often this formula is called the square root of the sum of the squares, because it's just this, that's exactly what it is. So you can use that formula to calculate the magnitude of any known vector. The last part of Cartesian vectors that you'll need to know is that for a given Cartesian vector, so we have a vector A, we could define vector A in terms of three angles, alpha, beta, and gamma, which relate vector A with the x, y, and z axes. All right, so we can relate all of these. We can define alpha, beta, and gamma using a cosine function. So the cosine of alpha is going to be equal to the magnitude of vector A in the x direction divided by the total magnitude of vector A. And it'll look like this on our diagram, where this is the angle we're just talking about. Cosine beta will define with being the ratio of cosine beta will be equal to the ratio of a of y divided by the total magnitude of y. So that will be beta here. And then our last coordinate direction angle will be gamma, which will relate the magnitude of a with the magnitude of a along the z-axis. So we can say that the cosine of gamma will be equal to a of z divided by a of z. Divided by the total magnitude of a. Okay, so those are our three coordinate direction angles, and then the one final thing we have in this video is that we can relate a unit vector to the directional cosine. So what that means is that for so what a unit vector is that if we can define the unit vector for vector A as being equal to vector A divided by the magnitude of vector A. Okay, now this is going to be equal to what this ends up being equal to is it's the same thing as dividing vector A by a scalar number. So what that ends up being is that's the same thing as A of x divided by magnitude of A times I plus A of y times divided by the magnitude of vector A times the unit vector j plus A of z divided by the magnitude of vector A times vector k. All right, so this is the coordinate direction. This is the definition of a unit vector, and we know that if we divide any vector by its magnitude, the magnitude of any unit vector has to be equal to 1. Okay, and if we go back to our definitions of our directional cosines, right, we know that a of x is equal to cosine alpha. A of y divided by the magnitude of a is equal to cosine beta. And then our third term, a of z divided by the magnitude of a is cosine gamma. So we also know that the magnitude of any vector is equal to the sum of all of its Cartesian components. All right, so if we take the sum of all of our Cartesian components, what that ends up being is cosine squared alpha plus cosine squared beta plus cosine squared gamma, which is the square of the x component of our unit vector, the y component of our unit vector, and the z component of our unit vector, all add together, needs to be equal to 1 squared, or needs to be equal to 1. So if you have any two of our coordinate direction angles, you can solve for the third coordinate direction angle if using this equality that we have on the very bottom here. Okay. So that concludes this video on Cartesian vectors in 3 dimensions.